Hey everyone, back in a new awesome video, and today we are going to continue with our series about electricity and magnetism. Today we will finish our exploration of the applications of Gauss Law. If you haven't watched the last videos yet, go watch them now so that you can understand every explanation. Today we are going to understand spherical symmetry. We'll first introduce a sphere. After that, we will understand what happens inside of a spherical cell, and we will end up understanding what happens with two spherical cells. So, let's start! Great! On our first video about Gauss Law that was done a couple weeks ago, we introduced Gauss Law for a point particle. Now we're going to give that particle volume and we're going to explore what happens with a sphere. If we have a sphere, the Gaussian surface we're going to use is a sphere. We know that the electric field is going to point outwards in the radial direction. In the spherical radial direction, not the cylindrical coordinates one. And our Gaussian surface, we will start with the region from the outside, is going to be that one, a sphere around our sphere. We are going to say that the radius of our sphere is going to be A, and the radius of our Gaussian surface is going to be R. Our flux calculation is pretty straightforward. We have the flux, it's 4 pi r squared, the area of our Gaussian surface, times the electric field. And the charge enclosed is going to be the volume of our surface times this charge density we have over there, volume charge density. So it's going to be 4/3 pi a cubed, as is that A, the volume of our sphere, times the charge density rho, all of it divided by epsilon naught. We see that we get some cancellations, 4 pi with 4 pi, and our result is E equals A cubed over 3 rho divided by epsilon naught in r squared in the r hat direction. We can see that if we multiply by 4 pi over here, we get the total charge of the sphere, and if we multiply over 4 pi over here, we would get a k factor and we would recover Coulomb's law. Now let's explore what happens inside of the sphere on our first region. To do so, we need a smaller Gaussian surface. We're going to take a sphere over here of radius r again. And now our flux calculation is going to be the exact same one. The flux is going to be 4 pi r squared E. But this time, this charge enclosed is going to depend on this r, not on a. Therefore, we're going to have 4/3 pi r cubed times rho divided by epsilon naught. Now we have some more cancellations. The 4 pi r squared with the 4 pi and 2 factors so far. And we get that E equals rho r over 3 epsilon naught. Now if we express this formula for all of, and in the r direction, sorry, for all of r, we see that we have rho r over 3 epsilon naught in the r hat direction for r less than a, less than or equal, and we have rho a cubed times 3r squared epsilon naught for r bigger than a. We see that if we substitute r equals to a in both of them, and the r hat vector, I keep forgetting them, if we substitute r equals a, we'll get the exact same expression for both of them, as this a squared will cancel with that a cubed, and we'll get rho a over 3 epsilon naught. And that is the electric field that a sphere creates. Now we're going to try and understand what is the electric field inside a spherical cell. If we have a spherical cell over here with total charge Q, a quick application in our mind of Gauss Law, for example on a spherical Gaussian surface over here, let's just see that actually there's no charge enclosed. Therefore, the electric field has to be zero. Now, I would like you to get some intuition about why that is the case. If we had a charge located at any point inside this spherical cell, for example, over here, we're going to have, there is two diametrically opposing zones. So this area over here is going to go like r1 square, and the area over here is going to go like r2 square, being r1 and r2 the distance to each of those zones. But we know that the electric field created by this blob of charge over here we would have at that angle is going to be proportional. So this is E1, there is a quantity proportional to r1 square of charge that is creating that electric field. But we know that that electric field is going to be proportional to 1 over r1 square. Therefore, we see that this is actually only proportional to 1 and other factors such as charge, the charge density, assuming that we have a uniform charge density. If we have, as we said earlier, that E2, we are going to have it proportional to r2 square, because it's a bigger blob of charge that is attracting our particle in that direction, in that solid angle. However, that electric field is going to have its intensity reduced by a factor of r2 squared in a similar manner. So it's really just going to be 1. It's not going to be proportional on distance. Therefore, this solid angle part is going to be cancelled by the corresponding solid angle on the diametrically opposing side. And therefore, all of the cell, all of the contributions of the electric field from the cell are going to cancel exactly, so that all the electric field inside the cell is exactly 0. Now that we have that intuition, we are able to understand what happens when we have two spherical cells. We can clearly see there's going to be 3 regions over here. We're going to have region 1, then that is going to be region 2, and this is going to be region 3. Let's try to get first an intuition about what is going to happen. We know that in region 1, this is just the addition of 2 cells, and we found earlier that inside of a cell, a charged cell, there is no electric field. Therefore, there is no reason to believe there is going to be an electric field generated by any of these two cells on the inside. Then on region 2, we know that this positive cell is not going to affect because of the same reason, because it's inside the cell and the electric field generated by this ring, this cell of charge is going to be 0. However, the negative cell of charge is going to create an electric field in this region. And then in region 3, we're going to experience the combined effect of the positive cell and the negative cell. Now, let's see what happens. As suspected, when we apply a Gaussian surface over here with Gauss Law, we find that it's 0, because there is no charge enclosed, and the electric field should be radially symmetric. Therefore, we conclude that the electric field has to be 0. Now, if we apply Gauss Law to a bigger Gaussian surface around region 2, which encloses this cell of charge, what we find is that the flux, it's going to be equal to the electric field times 4 pi r squared. It's going to be in region 2. It's going to be equal to Q minus Q times epsilon. Therefore, what we find is that E2, it's going to be minus Q over 4 pi epsilon naught r squared, which is minus k q r squared. And the n hat vector was pointing in the outwards, in the radially outwards direction. Therefore, we can stick that r hat vector over there. And what we find with this is that spherical cells also behave as point charges outside of their interior. Therefore, now we can try again to guess what happens in region 3. We know we are going to have a contribution from a point charge of minus q on the origin. And we are going to have a contribution from a point charge of plus q in the origin. Therefore, the total charge is going to be 0, and we are not going to have any contribution. We can easily check that by applying Gauss Law over here and finding that the electric flux in this region, in region 3, it's equal to the electric field times 4 pi r squared, and it's Q minus Q. That is the total charge enclosed, the positive part plus the negative part. So what we find is that this is equal to 0, as both charges are the same, and the electric field equals 0. So in the end, what we find is that the electric field generated by these two charges equals minus q over 4 pi epsilon naught r squared in between A and B. And that is what the electric field of two spherical cells is. That is all for today. I hope that now you have created a very good understanding of how Gauss Law works and how to apply it in different situations, taking advantage of lots of symmetries, and now you are able to use it in your everyday problems that you probably don't have relating to Gauss Law, unless you work on that field. Anyways, it was great doing these videos about Gauss Law, and we will now start in the next videos of this series with electric energy and electrical potential and some really interesting topics. Any doubts left, you may ask them in the comment section, and remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!